Welcome to Lab 4 on Oscillations. First, we'll discuss the introduction of this lab and the purpose. The purpose of this lab is to compare the motion observed in our video to the motion predicted by the computational model built in GlowScript. We also want to use the model to plot the change in kinetic energy, gravitational potential energy, spring potential energy, and total change in energy of the system. Result: we found that the system's total energy stays at zero, which demonstrates the energy principle. The system includes the spring mass system and the Earth, while the surroundings do not include anything. This means that there's zero work being done on our system and no thermal energy heat transfer. There are three main fundamental principles that we focus on in this lab. Like other labs, we continue to use the Newton's second law. We use this fundamental principle to update the velocity of the spring mass system, which will be used in other calculations. Derived from Newton's second law, we use the position update formula and velocity update formulas to move the spring mass system. Then, we also used the energy principle, which states that the change in energy of the system equals the work done by the surroundings plus heat transfer. In our case, the heat transfer and work will be zero since there is nothing in the surroundings. Here, the picture demonstrates the relationship between delta E, Q, and W. Here is the analysis of our observed motion in the tracker software. As you can see to the left, here's the video put into the tracker software. The picture in the middle represents the X and Y coordinates that we collected from the tracker software. We put these values into Excel and turn it into a .csv file. This .csv file will be used in our GlowScript computational model later. Here's the computational model. Here I display the initial conditions of the ball and the way we calculated the energies. The mass of the ball is 0.402 kilograms. The initial position of the ball is negative 1.108, negative 0.654 meters, and the initial velocity of the ball is 0.000 meters per second squared. These values are calculated from the tracker software using the first two positions. We also have the spring constant and the relaxed length of the spring, which we got from the video's character description of the mass system. Then we calculate the different energies. We calculate the kinetic energy using 1/2 mv squared. We calculate the gravitational potential energy by doing m times the gravitational constant times the position of the ball in the y component. We also calculate the spring potential energy by doing 1/2 times the spring constant times the total displacement squared. Then we add up all of these to get the total energy of the system. Here's the computational model continued. This represents the calculation loop that we use to update the position of the system using the position update formula and the velocity update formula. We also calculate each energy within the loop so that we can see the change in energy at each frame of the video and generate a plot of curves that show the change in energy of the system, the change in energy of each energy. Here's a graph generated from the computational model. This represents the x and y position predicted by the model and what was observed from the video. The discrepancies between the model and the prediction could be attributed to two possible errors. The first one is that the system is not truly isolated because the friction and drag force still leads to work done on the system by the surroundings. The second error is caused by the center of mass not being selected precisely by the user when analyzing the tracker video. Does the model and observed motion follow the energy principle? In the image to the right, we see the simulation generated by the computational model and the energy graph. As expected, since we chose the surroundings to be nothing, we see that the total overall change in energy of the system, orange line, is zero. Although there is a change in other energies like gravitational potential energy and spring potential energy, their sums equal zero, which is what is expected when there is no work being done on the system. Here are the x and y period of oscillations. Using the graph to the left, we can estimate that the period of oscillation for the x position is 1.7 seconds, while the period of oscillation for the y position is 1.5 seconds. We can do this by estimating the distance between each peak or each trough. This 1.02 second mismatch could be due to the camera angle in the video or the fact that we did not precisely find the center of mass of the spring mass system at every single frame. Thank you.